very happy to be with you today. Thanks for having me. Okay, I'm going to talk about Interstellar Lab and what we're doing on Earth and also in space, because we do both. So the company is 5 years old, started it in Los Angeles. We're a US company with a French subsidiary. My accent is French, but we're a US-based company. And so 5 years ago was this vision of what if we could use space technology to design a more efficient, closed-loop, regenerative approach for a food production system on Earth, or at least greenhouses, to make it simple, and how we can test on Earth system before we go to space and we help expand life into space. So the purpose of the company is to preserve life on Earth and at the same time bringing it in space. I'll explain. Okay. Why plants? Well, as you know, plants are the number one source of nutrients, flavor, bioactive. In the world, it's a huge market. Many of you are in this field, and it's growing very fast because everyone wants to have access to natural ingredients, so ingredients that are actually coming from plants. So there is a move from synthetic to botanical ingredients, even though synthetic is solving as well many problems that we're facing right now on Earth. So a lot of compounds across the food, the cosmetic, medicinal, pharmaceutical industry. We only currently using, all those industries are currently using only 1% of the molecule inside the plant. So there are still 90% of molecules that are in plants that are unknown. I'm not a scientist. I know there are many PhD in this room, so I apologize if I'm simplifying the science. What triggers the production of metabolites? In our case, we're mostly focusing on secondary metabolite, but what's trigger the production of this is biotic and abiotic stress. So if you simplify, basically if you control the environment and if you can play with it, you can trigger within the plants the production of specific molecules that are needed by different industries. So it means if you can control temperature, humidity, light, water, nutrients, microorganism, and eventually solar radiation and gravity, which are the two most stronger stress you can apply to a plant. And so what we're trying to do as a company is to provide a solution to bring a new solution to the supply chain of plant biocompounds, bioproduct, to this market that is in very high pressure, and because of climate change, geopolitical situation, but also because of the ESG constraint, where many of our customers on Earth, they're looking for more durable and sustainable solution. And so at Interstellar, by taking inspiration from a space station that we first designed in 2019, then we came up with a solution for our Earth customers, which is called biofarming. And so we are combining, well, everything that I'm passionate about, AI, not only me, it's a big team, AI, science, and hardware to create a solution to play with the environmental conditions so we can trigger the production of specific molecule inside plants. And to do that, we've developed controlled environment pods, completely sealed greenhouses. So greenhouses that you usually will not design for Earth because nobody was thinking of having a closed, sealed system on Earth because there is no reason to protect yourself from the outside environment, versus in space, you actually need a shield to protect yourself from the outside atmosphere because it's not livable for life. So by using this basic principle of a sealed, separate pod, we design a pod for Earth application. We combine that with AI that we've been training based on data we source from existing database of plants, where we find the species, the molecular composition of the species, and what is triggering the production of those molecules inside the plant. We turn this AI into programs that are running on all our hardware, and we adding what we call the bioscience, so the understanding of, I'm going to say not the truth, but how blue light plus CO2 at this level, plus adding a small microorganism at the root level, will trigger the production of a specific alkaloid that has a use case and application in the pharmaceutical world. So that's what we've been building, which is a platform, so not only a hardware solution. And both the two things that we're trying to do is, of course, to accelerate plant growth by playing with the conditions, so increasing CO2 and accelerating photosynthesis, doing water stress, but also playing with the microorganism to trigger the production of those secondary metabolites that we're interested. The core technology is the biopod. So this is the first pod we built a year and a half ago, and we've been using it since then. It's at our facility next to Paris. So it's much bigger than what you imagine. It's like 11 meters long, so it's 36 feet long, 17 feet high, and 17 feet large. The next generation that we are working on right now, that we're going to ship to our customers, is a little bit larger, and this one is not optimized inside. It's only 500 square feet of growing area on this one. On the second generation, is like 1,300 square feet growing area in a small compact pod. So it's completely sealed. The shell is based out of a composite, a polymer that we can recycle. The membrane is going to be fully transparent. This one is partially transparent. It's made out of ETFE, so it takes the light from the sun. So we use less LED and less power than any other greenhouses. You only need access to electricity to power, and otherwise you fill up the tank of water inside the pot and it reuse it. So it's made, so you have the ETFE membrane, it's a pressurized atmosphere inside, 400 Pascal above the atmospheric pressure, which creates a pathogen-free environment. On the top floor, of course, you have the AGS, the aeroponics growing system. We use aeroponics because we like to control the water stress, because water stress is one of the main factors that can accelerate or not the production of the molecule we are targeting. Inside the shell, you have the hydraulic and atmospheric system, the polymer shell, and a structural chassis. 90% of the water is recycled. We also have a CO2 scrubber. So we take CO2 from the terrestrial atmosphere to enrich the atmosphere inside the pod. We developed it very quickly. We assembled it very quickly, and it's been running for a year and a half, as I said. Those are some of the. This is a view from inside, so it gives you more of the in terms of the how big it is. Like humans standing inside of it. And as I said, the other part of the technology is not only the hardware, but it's really the integration with the intelligence. So this database that we build, and we leverage the existing database that actually has been developed by many universities, and the AI that we train based on this data we are gathering. So we have one biopod and 6 small, we call them biofarms, that have the same intelligence, the same software and sensors, and this is where we run all the science. And it works. We've been growing 40 species, over 500 identified on medicinal, pharmaceutical, and food. Those are some examples. When on average, on the 40 species, we accelerate the growth so it's a factor of 9, times 9. And then it really depends on the molecule you're looking for. I was mentioning alkaloid. We have a lot of here example on the perfume and cosmetic. Even though I know it's about food, but it's a first great go-to-market for us because they have a lot of money and they're struggling. The first 3 customers, Robertet, Firmenich, and L'Oréal, and we have great conversation with a lot of big companies here in the US. We're actually just signing with Cornell University, so if any representative of universities here, I'll be very happy to tell you about our program for research. Cornell is looking to use our biopod to, of course, to do research, and specifically on the production of, can be like vitamin C or like more on a focus on the food aspect, but how we can trigger the production of this by playing with the condition. Well, what they get, sustainable local production, exclusive and unique ingredients. You can predict, like, what you get from indoor farm, but sustainably, because current indoor farm has been criticized and for being having too much power consumption. The way we design it, we're really reducing the power consumption. What's the link with space? Those are some of the species we're growing. Different climate, you have an orchid, Edelweiss, which is an alpine plant, and then you have vanilla at the end. So very, very diverse species that we've been working on. And the plan as well install our solution on Earth. We have a big pipe for 2024, and we're currently building a biopod factory. So it's like a factory that's going to mass manufacture biopod. We're targeting 1 biopod every 2 weeks. The second step for us is to go on Earth orbit and then on the Moon and Mars. We don't have any contract for Mars yet, but we do have a program for low Earth orbit and a plan for the Moon, but 1 step at a time. Low Earth orbit and how to grow plants in a low gravity environment. Well, we apply for the NASA Deep Space Food Challenge that was presented before by HAF and the Canadian Space Agency, and we're among the winner of phase 1 and phase 2. We're currently working on phase 3. And so the system we've been developing for this competition is called Nucleus. So it's very similar to what I just presented, the biopod, except we had to meet the requirements that were given by NASA. Those requirements were, of course, the palatability, the modularity of the system, but also physical requirements. We couldn't do a biopod that was that big. So we reduced the same approach into boxes. So Nucleus is composed of 6 growing quarks. Each quark has a different controlled environment, so exactly the same software that we're using for biopod, where we recreate the climate, but we optimize the condition in between the quarks by using the CO2 that is produced by the insect to feed the plants. So it's kind of a small closed-loop system. It's like a small biosphere, but divided in boxes, but a very small biosphere. So we have 3 quarks that are dedicated to plants, 1 to mushroom, 1 to insects, but you can, and then another 1 to vegetables, but you can actually, they are modular, so you can change everything inside and just adapt the climate, and then it will grow and leverage and rearrange the setup of the climates. We built the first prototype, which is currently sleeping at Kennedy Space Center, because we're building the second one right now. On the second version, all the modules that you can see, the white boxes, they're all going to be 3D printed, because this is things that we do as well. We have large printers and we 3D print, so we can really have a system that eventually on a space station or a future on the moon, you just go with a robot, and the robot can like 3D print all the system. That's the long-term vision. This is the one step at a time. But this is what we've been proposing. This is what we envision for future space station. So how you can put the system there. So it looks like small microwave in a sense, but they will all have their private climate. And you can really play and found one of the main things also that we've been focusing on is the reducing crew time, and so the same AI that we developed for the biopod, we've been applying it to Nucleus. So as in the company we have a mission control. We can see all the hardware that we built. We can take control in case something wrong is going on, but they have their own intelligence and they're running by themselves, understanding what they're growing inside, and we're just following what's going on, trying to minimize the humans so they don't need to plan and do everything. Those are some pictures of the first prototype that we built with some of the microgreens that we've grown. On the mushrooms and also on the insect. On the insect, it's a tricky one. So we choose black soldier flies because we had to recreate a system where it will recreate the entire life cycle of the insect. So we created a love room. We 3D printed those small balls so they can put their eggs. And then you have the larvae, and then they degrade the biomaterial that is left from the unedible part of the plant, and then it goes back into a cycle. It's not designed yet to fly. It's like part of a process. What we're really focusing on with this prototype is to test the intelligence, the automation, and see how we can really balance the use of resources. Mission Little Prince is the latest mission we announced a few months ago, just after the last Starship flight. It's a commercial mission, so it's not something that has been designed by a space agency. We're designing the mission, and we secured a flight on SpaceX Starship with Astrolab. So it's going to be the first Starship commercial flight to the moon. And we're going with Astrolab, which is building this rover that you can see, and we are developing the little pod. Of course, it's a conceptual design. We haven't done the design review yet. And what we're building is this pod that you can see on the first part of the image, on the front of the image. I'll show you. So the whole purpose, the flight is secure for end of the window is end 26, early 2028. Personally, I think it's more going to be 27. And the goal is to grow a flower on the moon. There is, of course, a scientific objective of it. It's to measure the impact of a lunar environment on how a plant is growing. But there is also a very inspirational mission that we are trying to do, and especially with the title Mission Little Prince. I don't know if you know about the book, but it's very inspired by the book. It's not official, but I can tell you because we agreed. But we have the family of Saint-Exupéry, the nephew. They're backing the mission. They're an official supporter of the mission. And together we'll try to promote this mission all around the world. It's really to inspire, and so people can look at space as I think we need to bring a little bit more poesy and beauty in what we're trying to achieve with space exploration, and so we can all align in this. That's just a teaser of what's going to be the mission about. I call it reverse WALL-E as well, because this time the rover is not looking for life on a planet, but is bringing life. So it's not a manned mission. Will be no astronauts. But so Astrolab rover will carry a payload and will install the payload on the surface of the moon. There will be a camera, of course, to film everything that is going on. There are some activation with kids in school that we're working on, but we're not telling anything now. And we really want to take this picture, maybe not like this one, but the picture where you can see the Earth rise on the back, the lunar surface, and a plant growing. That's us, not all of us. Since this picture, we have 15 more people in the team. But voilà, I'm happy to take any question about Interstellar. Thank you for your attention.